Good morning. I'm Ben, and I'd like to talk today about a transient semantics for typed Racket. And this is something I've been working on with Lucas and Christos from Northwestern and Matthias from Northeastern. And we recently published this work in the Programming Journal, Volume 6, Number 2. So first things first, this work is about gradual typing. And so we're on the same page. Gradually typed language is one where we can mix statically typed code and dynamically typed code, or typed and untyped for short. Here's a simple example. We've got a typed function named add1, which says it expects one input n, and that n has static type number. And then down below, we have some untyped code, which is calling the function, sending add1 a string, hola, instead of a number. So we want to be able to write programs like this in a gradual language. And now a main question is, what do these static types mean when the program runs? So people have looked at this question for many years now, and three strategies have emerged. The strongest one, guarded, is to enforce these types with higher order contracts or with full traversals. And these let you, as a programmer, you can assume that the full behavior of the type is going to be enforced when you run the program. The transient strategy doesn't use these wrappers. Instead, it has lightweight checks spread throughout typed code, and these enforce types as kind of spot check throughout the program. And then third, the optional typing strategy says these static types should only be used for static analysis, and they shouldn't have any effect on how the program runs. So no wrappers, no spot checks, no checks whatsoever. So these are three strategies: guarded, transient, and optional. To go back to our first example, guarded and transient both agree that this code should give an error when it runs because add1 received a string and it expected a number. Optional types say, okay, this is no problem. The result is whatever is the result of adding hola plus 1. Here's a slightly more complicated example. We have an untyped data structure, this array R, which has a string and a number inside. And now we send that array into a typed client, which is expecting an array of numbers. And then the typed client acts as the first element of the array called nums, which is really our untyped array. What happens here? Well, guarded and transient still agree. They both say this program should give an error because we expected an array of numbers, and that's not quite what we got. And optional says the result is whatever's the first element inside the array. But now, just to show you how guarded and transient differ, if we modify this program slightly, we get a different outcome. So here we have the same code as before, but we've moved the third line that access num0 over into untyped code. So we start off with an untyped data structure. We send it through a typed interface, and then send it back out to an untyped client, which accesses the first element. In this case, guarded is the only one that gives us an error, and both transient and optional say the result is whatever's sitting there inside the first element of the array. So we have these three different strategies. Myself and my team, we've all been working in the context of guarded, specifically in a language called typed Racket. It's got these types and it's got a problem. The trouble is that guarded types can become really expensive in a large program. So as I said before, guarded has strong types, and in particular, it satisfies these two formal properties, type soundness and complete monitoring. And sad to say, the gradual typing benchmark suite that we've been using, GTP benchmarks, high overheads for mixing typed and untyped code are very, very common. And these are big numbers for the overhead. We're looking at 25x compared to the untyped version of the program, or in some cases, 1,000 times slower than the untyped version. So these are unacceptable. And this is why we started asking questions like this. Is sound gradual typing going to work at all in practice? Because if the promise is you can mix code any way that you want, but the reality is you're going to have to pay a huge cost for it, well, that's just not practical. So we have this problem. What can possibly be done now? Well, one idea to lower the cost of guarded types is to just write better code. Maybe we can improve the compiler that we have in some way. Collapsible contracts was one project that pursued this line, and it did extremely well. We had an asymptotic improvement in the costs. But unfortunately, there's still other huge slowdowns in the compiler, and we don't have any other asymptotic ideas about how to get around them. So I think this improving the compiler is running out of steam, and guarded is still slow. Another option is to try to remove checks with a static analysis. There's a lot of redundancy in these checks, especially when we have a 25x slowdown program. And so an analysis like Corp Survivor helps lower these. So this is definitely one viable option. Another is to build an entirely new compiler that leverages different technology. And related to this, you could also consider a new language built from the start to support gradual typing. So Picket is one example of a new compiler. It uses tracing JIT technology, and it also does a good job at removing checks. What I want to tell you today is about a fourth option, which is instead of going all forward unguarded, we can use different weaker types instead. And so that's what we've been working on. Now, why do we want this, especially when we have option 2 and 3, which are certainly decent options? Well, if we add weaker types, we can reduce the costs in our language without changing the programmer experience at all. You have the same code, same workflow, and in particular, the same static type checker that you had before. And the only thing that changes is some of your types have different runtime behavior than before, different semantics. Okay, so that's the idea. And the pioneer that we're using as inspiration is reticulated Python, which reticulated was the context of the original implementation of Transient, came from Indiana University, and it was a big part of it. No, it was the focus of Michael Batusik's dissertation. So Michael and several other people helped implement reticulated with Transient. Now, again, the idea with transient semantics, transient types, is to use tag checks throughout the program to enforce a weak kind of soundness and no contract wrappers. And this was inspiring to us because they evaluated Transient on several benchmarks, Python benchmarks, and they found the performance was not at all bad. In the worst case, they saw a 6x slowdown for these transient checks alone. And when they turned on something called blame, the overhead went up to 18x. So still, compared to guarded, this is not bad at all. So now we come to our research questions. At a technical level, we are asking, how can we add transient types to typed Racket? Now, this work is not just about typed Racket and the specific compiler. There's two broader questions that are interesting for the community at large. First is, Transient's been implemented for reticulated, but can we scale it to a larger and richer type system like the one we have in typed Racket? Second question is, can we implement Transient without writing a new compiler from scratch? Can we do so by adapting the compiler that we currently have? And right, the answers to these questions are important for the broader community. And I especially want to call out optionally typed languages. So these are gradual languages where the types are currently unsound. And we think that adding Transient to an optional compiler, such as TypeScript, might be a promising way to strengthen the types and add a form of soundness at a low cost. Now, for the context. So we have two type systems sitting here, from reticulated and from typed Racket. The types in the reticulated paper are the first four here on the left: dynamic type, integers, reference cells, and simple functions. So this is exactly what you want for a basic gradual lambda calculus. Inside the implementation of reticulated, there's a few more types, and I especially want to call out structural class types, structural first order classes. Okay, but then that was about it. There's a few other types for Python data structures, but there's several things that are missing that we have in typed Racket on the other side. Okay, so what's on the right? First, there is no dynamic type in typed Racket. Instead, we have a top type called any. And so as a programmer, I can upcast anything to the any type, but if I want to downcast it, there's going to be a wrapper involved, and that might not always work. So it's less flexible than your dynamic type. Also, that top type means that we have subtyping, and the subtyping manifests itself in the base types. So just as one example out of many, we have type integer and type natural as two ways of describing numbers. And these types are subsets of one another. Natural is a subset of integer, and that comes out in the subtyping relation. So that's another thing that we need to worry about. There are many data structure types, but there's also homogeneous data structures and heterogeneous data structures. Here, this vector t describes an array where all the elements have a common type. And the second one, vector t dot dot dot, is a vector with a fixed size, and each slot has a particular type assigned to it. Typed Racket also has function types, but there are many more details involved with the function type. The function can take in optional and keyword arguments, and a function can return several values, not just one. We also have, we have first class and object types. And then on top of that, we have these type connectives, universal types, all, union types, which refer to untagged union, and recursive type, rec. Okay, and there are several others. So it certainly wasn't clear at the start whether the reticulated strategy would be able to handle the types on the right. And second, if it could handle them, we weren't clear what the performance cost would be. The second part of the context is we have two compilers. So reticulated was a from-scratch development built on top of Python. So there's one pass in the reticulated compiler, and it's simultaneously type checking the code, making sure that the types are valid, and elaborating the code down to Python. So this is using the static types that we just validated to insert a runtime check into type code. So these checks get spread throughout. And these two parts, type check and elaborate, work in tandem. They go back and forth in the one pass. Now in typed Racket, before Transient, we have several passes here. First, before anything happens related to typed Racket, the source code of a typed Racket program gets expanded by the Racket macro expander. This brings us down into a kernel language, and that's what the type checker runs on. After type checking, there's a pass to guard boundaries with the wrappers that we mentioned before. So this is where guard kicks in, and that's to protect our typed modules from untyped code that it interacts with. The next pass is a type-directed optimizer. And then after that, the final semantics of a typed Racket program is the Racket semantics of the generated code. So ideally, what we'd like to do here for adding transient is to change only the guard pass. Everything else, expander has to stay the same, type checker should stay the same, and optimizer and Racket, we'd like to reuse those as well. So can we slot out that one pass and insert this other one? That's the question. And it can be done, but there were many bumps in the road along the way. So let me just quickly describe what we ran into. First, how do we enforce these different types? Well, the main takeaway is we can't do so with simple tag checks. We need to be a little bit more sophisticated. We're using what we call shape checks, and that's taking a name from optimizing compiler technology like self. So shape, our idea, we're validating the full constructor of a type. As soon as we get down to a type that describes a class of values, check the first order aspects of it, and then nothing more. So the paper has lots of examples for this, but we needed to generalize these tag checks to shape checks. And once we'd had that, we had something we could move forward with. The next question was, what do we do with the optimizer? And in particular, the typed Racket optimizer was assuming full types in some of its passes. So these needed to be toned down. We can only trust the things that we validated when the program runs, and these are the shapes that we're checking now with our transient. We were surprised to find out, though, that by checking full type constructors, checking these shapes, we were able to keep many of the passes. All but two we were able to keep. Another challenge is, how do we navigate the expanded code? The source code of a typed Racket program is not the code that the type checker runs on, and there can be many more forms inside this. So in general, we needed the type checking pass to leave behind evidence showing what did it validate about a program and what did it not validate. And we use that evidence to power the transient pass that comes afterward. And finally, a cross-cutting concern was, how do we minimize the runtime costs of this transient semantics? So choosing the shape checks and making sure that the optimizer ran correctly with both parts of the puzzle here. But another big aspect was making sure that we generate efficient code. So wherever possible, we want to reuse the definition of shape checks and just make sure that we're generating trim code throughout. Let me zoom in for a minute on the one challenge of navigating expanded code. At the top left here, we have a for-sum combinator. So this is a tiny program. It's looping over every byte in a file, and it's adding those bytes up to get one large number. This is the source code. When we expand this program, it gets much, much bigger. So here we have this huge mess where the for combinator gets turned into a recursive function. And the quick takeaway here, a naive implementation of Transient would say every function call inside this expanded program potentially needs a check to make sure that it didn't return incorrect data. But some of this code is it's not code that the programmer wrote. It's not a place where untyped code can slip in. It's the expanded semantics that comes from the internals of the Racket compiler. It comes from a trusted part of the code base. So this is why we need the type checker to record what evidence. We need evidence from the type checker to say what types are the vulnerable ones. And we use this to guide the checks and reduce the ones that we're executing at runtime. Okay, we certainly don't want to check every function call sitting here. Okay, but with these challenges accepted, challenges passed, we built a transient semantics for typed Racket. Next question is, how does the performance turn out? And does it match what we were seeing for reticulated? Did we meet these goalposts, 6x overhead for the checks and an 18x overhead for the blame turned on? And I still haven't told you what blame is, but we'll get to that in about 2 slides. So let's look at the worst case overhead that we see with transient typed Racket compared to untyped. So for transient checks alone, we're doing very well. Here we have the names of the 21 GTP benchmarks. And we see for all but a few, we're within that 6x threshold. And some of these numbers are very good. I mean, a 1x worst case, it's 1x rounded down, I think. This is not bad at all. 1x, 2x, these are good, and they might be able to get even better in the future. There's a few that are slower. So we see Snake, Tetris, and Quad. Snake, Tetris, and the 2 quads, they're all within a 10x, which is not bad, but could be improved. The one real down point is Zombie. This one has a 31x slowdown, and we attribute that to a large number of function calls sitting in typed code for Zombie. So this is the trade-off that we have with Transient. Every expression that you have in a typed program pays a small cost, and these costs add up. And in the case of Zombie, we think they're just adding up to be a bit too high. So we'd love to reduce this 31x, but still, in general, we're happy. Now, what about blame? Well, this is the bad news. Transient with blame is extremely slow on these benchmarks. So now let's step back for a minute and see what is blame, and then we'll get into why it's so expensive. So recall, we're in a gradual language. Our program has these typed and untyped blocks of code, which are communicating with one another when we run the program. So we might have, for example, an untyped function that travels into typed block, travels out to untyped, and back into typed again. It takes a path throughout the program. In this case, we have a function that returns a string, b. We're sending it to typed code in the second block here and giving it an incorrect type. We're saying our untyped function has type number to number. So this is not going to work out. When we call the function, we will find a string, not a number. So this program will error when we eventually call it in typed code. So the idea with blame is to say, when one of these errors occurs, can we trace it back to one boundary early on, or maybe one set of boundaries, and give the programmer some idea of where do you start debugging to find out what's the source of this error. So with guarded types, the strategy for blame is to, well, first of all, we're going to wrap values with guarded. And then for blame, we can attach metadata to these wrappers. The metadata tells us what boundary to look at. So now if a wrapper detects a problem, we can point back precisely to one boundary where to start debugging. With Transient, we don't have wrappers. So what do we do instead? Well, the idea from Vitusek and folks at Indiana was, let's keep a global map on the side of the program. So this map has an entry for every higher order value that we create. For example, there's an entry for this function. And now every time these values cross a boundary, and every time we use these values, we can update the map and do a little bit of bookkeeping. And what we're seeing is this map is just too expensive. It gets too big too quickly. Yes, and that is why we're seeing these overheads of 100 or more. The ones that say greater than, like the first one, KCFA greater than 540, that's because we timed out the benchmark after running for 10 minutes. So it's at least that much slower than untyped. Why are we seeing these huge numbers when reticulated saw a worst case of 18x? Well, we looked into this in some detail, and we have two explanations. One is that our benchmarks are simply larger and they make more values and they spend more time computing. And that blame map keeps sitting there and growing bigger and bigger. So even though the map holds keys weakly, we believe it's still inhibiting the garbage collector, and it's definitely a lot of operations to maintain the map. So that's where this cost is coming from. Also, to confirm this conjecture, we ported one of our benchmarks, Civ, back over to reticulated, and we saw it was also extremely slow and reticulated. So we think this is definitely a fundamental cost. Now, reason two is a bit more subtle. Remember, we don't have the dynamic type in typed Racket. And instead, we have a richer type system, which is assigning types to every expression in typed code. So because we don't have dynamic as this catch-all or this fallback, and we have these precise types instead, there's a lot more places where we need to update the blame map. So if something has type dynamic, then you don't need to update the map. There's no bookkeeping for that. But as long as it has a type, whatever it is, we have extra bookkeeping. So that's another reason why we're paying more than reticulated does. Right, but our takeaway in the end was, look, this was one challenge that we were not able to overcome. We believe that transient blame is just too expensive. We either need a different strategy, but it's also, let's leave open the possibility. It could be that future work adding specialized runtime support for the blame map might make it work out. It might reduce these costs. So that, we shall see. Yeah, personally, I think the blame is too expensive. But now I want to emphasize again, with transient alone, transient without blame, we're very happy with the performance. And let's look quickly now at the overall picture, not just the worst case. So first, what is overall? We're in a gradually typed language. Overall means we care about all possible ways that we can mix typed and untyped code. So if we're sitting in a program that has 3 components in it, there's 2 to the 3, or there's 8 configurations that we care about. They're arranged here on the left as a kind of lattice, where the point on the bottom is the totally untyped version of these 3 programs. The point at the top is the totally typed version. And then in the middle, we have all the ways of mixing. So we're interested in what's the performance of each one of these, because if we give programmer access to gradual typing, they might want to use any point in this configuration space. So now we represent the performance using a plot like this one on the right. The y-axis is counting configurations out of a lattice like this one. And the x-axis shows different upper bounds for what is too slow performance, or another way, what's good enough performance. So if we zoom in on one point in the x-axis, say x is 10x, so we're willing to accept a 10x slowdown, then what we do is look over the lattice and see how many points meet the 10x mark. And in this plot, we have about 1/8 of all the points are within the 10x. And so we see something like there's 2 checks and many x's. So these 2 points we can use, and the rest of the points are too slow. The bottom line for a plot like this one on the right, you want to see a larger area under the curve. Larger area means better performance. So now let's look at some more of the benchmarks. Here's 6 plots from 6 benchmarks. These are blue curves, and they all represent the performance of guarded, so standard typed Racket. If we're willing to tolerate slowdowns between 1x and 20x, what percent of all the points, going from 0% to 100%, what percent of these can we use? And we see for all of these, if we're willing to tolerate even something as slow as 20x, we can use about half of the configuration points. So that's not very good. Let's overlay transient on top. With transient type Racket, we have this beautiful sunrise coming up over the horizon, right? Lots and lots more points become usable at much lower overhead. So gradual typing is feasible to a much bigger scale than it was before. Many more points run faster. So this is great news. Shows overall getting much better. But it's not the case, surprisingly. Transient is just the winner. Look at Dungeon on the bottom right, and especially look at the 2x mark for Dungeon. It says more of the guarded points run within 2x than the transient points. And that's because guarded does extremely well once we've taken away these typed untyped interactions. So If there's a typed module talking to an untyped module and they're doing lots of back and forth with lots of big values, guarded pays a high cost. But when that critical boundary has types on both sides, the cost suddenly goes away. And then guarded also gets the full benefit of type-corrected optimizations. So there's really a trade-off here. Transient is the best when we have lots of mixing typed and untyped. It's got lower costs in general for that. But guarded is the best choice once our program is mostly typed, or once all these critical boundaries have types on both sides. So we think in the future, both strategies are important to have access to. And now the question becomes, how can we navigate a space where we have two semantics for types inside of our gradual language? So this is an exciting place to look at for future work. Now, to wrap up, we had asked, can we have transient types move over to typed Racket? Can we scale them to a rich type system? And can we do so without throwing out big parts of our existing compiler? And the answers to both are yes, as long as we're willing to go without blame. And for us, that's totally fine because you can always switch back to the guarded types, and then you have precise blame information for those. And also, we needed to do a bit of engineering as well to make sure that Transient worked out for typed Racket. But I'm happy to say the experience worked out. Overall performance is much improved, and we're glad to recommend Transient going forward. Now, I want to end by reminding about the point that I mentioned earlier on. So our motivation for adding Transient was to lower the costs of guarded. We weakened the types, and we wound up with faster performance. But it's also an interesting choice for these optional languages. If you'd like to strengthen the optional types sitting in TypeScript or in one of the many optional languages for Python, we think Transient is going to be a great compromise for doing that. And our experience with typed Racket suggests that you can modify an ahead of time compiler, just adding one extra pass to insert transient checks. And now you should have a low cost way to add soundness to the program. So that's the end of my talk, and thank you all for listening. I do though. So normally we would take question and answer now, but it's just me here. I do though have some extra slides. So let's quickly go through those. And after that, I'll point you towards the paper. So check that out. First, here's the full table of all the worst case overheads. We've got transient and transient blame that we saw before. And then for comparison, we have what's the cost of guarded. And it's interesting that guarded is a lot faster than the worst case of transient blame. It's not always. I mean, in some of these benchmark, guarded is awful. But yeah, we were shocked and amazed that guarded was faster than transient blame. And that's part of why we think that the transient blame strategy is not going to work in the long run. Here's a quick table of all the optimizations in typed Racket and whether or not they work with transient. Only 2 of them we had to turn off because they were using deep types that go beyond the shapes that we were checking. And if you'd like to learn more about that, please check out the blog post linked below. Okay, when I was talking about why blame was slow, why our blame was slower than reticulated, I mentioned the dynamic type. And here's one example from a reticulated benchmark. The benchmark is called N queens. And in this case, dynamic really saved reticulated a lot of time with the blame map. The key here is we have a main function as part of the benchmark, and it's got this while loop, which is doing a lot of the computation. The while loop is mutating a bunch of local variables, and the key ones are indices, cycles, and result. And these all have the dynamic type. And now because they have the dynamic type, they were much cheaper for the blame map. So it was an interesting consequence of type inferencing reticulated. And we were surprised that it wound up saving costs for the blame map. But that's just what it is. And please contact me if you have more questions. Okay, in addition to giving better performance, having the transient semantics for typed Racket can also let us run some programs that we weren't able to run before. This is one example of that. We've got on the left typed code that creates a box. So this is a mutable reference cell. Gives that box the type any, that's our top type, and then sends it over to untyped code. It's a box with a character inside. That's on the left. And now on the right, the untyped code is trying to update the box with set box, putting a new character in the box. So that should be fine, right? It's a box of characters. We're adding a character. Or changing the character on the other side. But with the guarded types, this gives us an error. The reason for the error is that any, as the top type, has to be a very strict wrapper for clients. Transient, there are no wrappers. So this write goes through and it's not a problem, the program runs. And so this is one example of what I mean of how Transient can give us simpler semantics. And in some cases, it's the semantics that a programmer would prefer. Okay, and finally, I want to acknowledge one limitation. It's a limitation in our Transient, but it's also a limitation inside guarded. Typed Racket has these fancy types called occurrence types, and they allow flow-sensitive reasoning. The program down here uses occurrence type. So statically, this program is just fine. It type checks, and I'll walk us through it in a minute. But dynamically, we have to reject it at the first line. We have to reject where it tries to import a function identity and assign it an occurrence type. Now, both guarded and transient have to reject it because they don't know how to enforce the occurrence type. And it's a big question of how we could allow this in the future, how we could enforce it and let a program like this run until a later point, until we're certain that it's going to have an error. With guarded, it's really not clear to me how we would do it. With transient, I think it can be done with a more sophisticated, flow-sensitive rewriting pass. So now let me step through the program. Line 1 says require from the library Racket/function, require the identity function. So the behavior of this identity is it takes in one value and returns one of the same value. But we give it this funny type. We say identity takes in anything. It always returns a Boolean, and it returns, yeah, that's fine. And okay, takes in any, returns a Boolean, and it has this occurrence type string. So the occurrence type says if the result is true, truthy, then we know the input must have been a string. And if the result is false, we know the input is not a string. So that's this flow sensitive thing. Depending on what the output value is, we learn something about the input. That's what the occurrence type says. That's not an accurate description of the identity function. But because we're in a gradual language, we want to be able to make claims like this at a boundary, because the claim might be about untyped code that we're suddenly adding a typed layer on top of. Now, the next line of the program says x is a variable with type any, and it has the value 0. Now we're defining a fake string with type string. And we're defining it first by calling identity on our x. So call identity with 0. This will return 0 again, and that's a truthy result. So we should wind up in the first case of the if branch. And that's why the second case says unreachable. And if we're in this first case, the occurrence type lets us conclude that the input to identity just above must have been a string. So the occurrence type refines that x type any down to x having type string. So that's how we're able to get a fake string here. And then if this program could run without raising an error up until the final line, then we would be taking the length of the number 0, take the string length of 0. And that's not good. When the type-directed optimizer runs and replaces that string length with a fast operation, it's going to do undefined. We're likely to get a seg fault, taking the string length of 0. So we want to catch this program early. And then, yeah, unfortunately, the limitation is both guarded and transient have to stop it right at the boundary. They can't allow identity to cross or anything to cross with an occurrence type. We stop it before. So now that's all the extra slides. I'll put a link to the paper down below. And thank you again. You all have a great day. Bye-bye now.